All right. Okay, so good morning. So since I'm the first speaker, I'm going to take this opportunity to say a few words about the scope of the conference and talk on the behalf of the organizer, Corey and Greg. So the objective of this workshop is to exchange ideas on the fracture and physics of disorder solids and related topics. And we are lucky to have a rather broad range of participants from different communities, from theoretical physics, condensed matter physics, mechanics, geology. So I count on all the speakers to provide pedagogical talks accessible to this broad audience. Also, I would like to encourage questions during talks. So we have scheduled 15 minutes for discussion after each talk. Don't hesitate to use this time to interrupt speakers and ask questions. So I hope we'll have a great conference. And let me start with the first talk. All right. So what I would like to discuss for the first presentation of the morning session on fracture is a new development in the statistical description of fracture surfaces and the interpretation of the scaling properties of fracture surfaces in terms of failure mechanisms. So I would like also to broaden the perspective and also discuss the relevance of scaling concept, universalities that has been largely used in this field for understanding the process of failure of materials. So 30 years ago, Mandelbrot and co-workers brought out the scale invariant properties of the roughness of cracks. And so it might be this work, this pioneering work, has triggered a large amount of research work until now to try to interpret this feature, make sense to these scaling properties, and provide insight on the fracture of material from the scaling properties of fracture surface. So I will take this opportunity also of this talk to look back and see if this research direction has been fruitful, and hopefully we can discuss more about it in the discussion part of the talk. So along this line, Mandelbrot at this time argued that the fractal exponent of fracture surfaces that is represented here was correlated with the fracture energy of the material, and actually a few years later, it was shown that by Elisabeth Bouchot that the fractal exponent or the self-affine exponent is actually invariant and independent of the material properties. But I will come back on this tentative to connect scaling properties with fracture properties, and in particular material fracture toughness. So to address fracture problem, there is actually a very powerful predictive theory called linear elastic fracture mechanics that is used on a daily basis to predict failure in engineering structures. And this theory rests on an energy balance, and within this theory, you describe fracture as a transfer of mechanical energy into dissipated fracture energy. Within this framework, it is convenient to define rate of energy as a crack propagate over some infinitesimal length scale, and you're going to define a driving force for crack advance as the rate of energy released, mechanical energy released as a crack propagate, that contain both the work of the external force injected in your system and the elastic energy stored in your solid as the crack propagate that is released during crack propagation. And you compare this thermodynamic driving force with resistance to crack growth, that is the rate of energy dissipated as the crack propagates over some unit surface. So from it, you can predict crack propagation. You can say for a given loading that affect G, if the crack propagates by comparing to GC, that is an intrinsic material property. But the weakness of this approach is it doesn't give no hint on the value on the actual value of the fracture energy, simply because this is a continuum mechanics based theory, doesn't provide any information related to material macrostructure, material dissipation, and microscopic dissipation mechanism. To get some insight into the value of fracture energy of material, then you need to look at the actual failure processes at the crack tip. And you can look at that in different materials. You see rather a lot of complexity when you look at the proper length scale in different materials, but at the same time you also see some common features where you see clearly discontinuity of the crack propagation that looks more like a process of damage coalescence at a length scale that depends on the material you considered. So the way I'm going to explore this mechanism is to look at the fracture surface. And the hope is that this dissipative, the information of this dissipative mechanism is encoded in the age fluctuation of the crack as it propagates through a material. So the challenge will be first to provide a statistical description of the roughness of crack, and then to interpret them in terms of failure mechanism in dissipative macroscopic mechanism. So the goal of this presentation and also the outline of this presentation will be to provide a complete complete description of the roughness of crack through materials, keeping only properties that actually are not material dependent. And in particular, we will see that scaling properties can be robust, to use them to explore this macroscopic mechanism and also, if possible, from a more engineer perspective, to use them to trace back the history of fracture of material. This is classical fractography. I will start by some review and some recent advance in the understanding of the scaling properties, and focus on the value of roughness exponent that I will define further. That will help us to define two classes of failure mechanism corresponding to persistent and anti-persistent crack path. In the second step, I will go further than the scaling properties, and we will discuss the full statistical properties of crack surfaces, that will give some insight, also some deeper insight on the mechanism responsible for crack roughness, and will provide insight also in more on the fracture of materials. To finally say a word on application of this work in the characterization of failure of material by post-mortem analysis of fracture surface. This topic being addressed further by Alan Edelman at the end of this morning session. So the idea of Mandelbrot and several scientists after him was to use the morphology of fracture surfaces like this one for an aluminum alloy to get insight onto the fracture processes. And the idea was to look at the correlation between age fluctuation. In particular, a practical way to do this is to use a two-point correlation function, where you're going to compute the typical age difference between 2 points distant by delta z, defined by this way, this correlation function, defined as the square of the 8 difference average over the surface. And if you represent in a log logarithmic representation this correlation function, you observe power law behaviors and characterized by an exponent 0.75 about that is very robust and doesn't seem to depend on many features, in particular on materials and loading conditions. If you go a step further and investigate scaling properties in different directions, in the front propagation direction and in the propagation direction, you see a slight anisotropy, a dependence of the exponent with the direction, and you can actually show that this surface is described fully by the scaling property of this surface is fully described by 2 different exponents. A bit after, confirmed by more recent experiment, other type of fracture surface could be revealed. In particular, in brittle rocks or brittle ceramics, fracture surface were shown to display also scaling behaviors of the correlation function, but with exponents that are smaller, in particular equal to 0.5 or below. And here also, there are slight anisotropy of the surface, but the set of exponents is clearly smaller. And in this example, it was shown, for example, that this doesn't depend on the grain size or on the porosity of the ceramics investigated. So this this amount of result over the year led to the conjecture or to the scenario that there are 2 classes of scaling properties. Some class of roughness associated with brittle failure with small exponent, and another class of fracture surfaces that will be associated with damaged coalescence processes. So it's relevant to simplify to look at these classes of scaling properties. It's relevant to simplify the problem and look at a simpler system, a 2D fracture in 2D thin sheet. In that case, instead of having a full 2D fracture map, you have only one profile that is representative of the trajectory of the crack, for example, in a sheet of paper. And if you compute here also the correlation function of this crack path, you can observe a scaling behavior characterized by an exponent of the order of 0.65, mainly in a sheet of paper that has been largely used by several authors, here in the example of 3 different types of papers. And interestingly, you can also, like in 3D, identify on 2D system where the exponent is also lower, another class of roughness. And a good example is to take an expanded polystyrene sheet. The idea to observe this smaller exponent is to consider a material that have a clear scale separation between the dissipative processes that we discussed at the beginning, that takes place at some length scale, and some microstructural length scale, typically a grain size. And this is precisely the case in the polystyrene thin plates, since you have a millimeter scale grain size. And in that case, the scaling properties of the roughness are characterized by an exponent close to 0.5, and you can show that the properties of this crack path are really reminiscent of a directed random walk. So you can confirm that through numerics, through simulation, and simulate the process of failure of consolidated granular material, making the assumption that the cohesive zone or the dissipative zone is very small with respect to the grain size. Through remeshing technique, you can obtain very long crack path that also exhibit statistical property characteristic of directed random walk. So let me summarize all this experimental observation in this table, where on the rows I have given the result for 2D system and 3D system, while the columns have separated both into the columns into anti-persistent crack paths with exponent close to 0.5 or smaller, and persistent crack paths with larger value of exponent. And so it is tempting to associate these classes to different failure mechanisms. Brittle failure, when dissipation mechanism takes place at much smaller scale than the scale at which we observe this exponent, and failure by damage coalescence. And actually, to support this scenario, there are several theoretical work that can explain quantitatively the value of exponent. In these cases, we can understand qualitatively the value of exponent by developing models of crack propagation, brittle crack propagation in some disorder field of toughness, or a randomly distributed array of defect, while this exponent can be also explained using a different kind of model based on damage coalescence processes. These exponents are not clearly understood yet. So the question, first, to understand qualitatively the value of this exponent, we can provide a hand-waving argument. If you have a crack propagating straightly and then being deviated due to some material heterogeneity, you can ask what will be the next propagation direction of this crack. And if you have a crack growth direction governed by elasticity, you expect the crack to go back to the straight direction, while if you have a crack growth direction governed by damage nucleation, you have a crack path attracted by the damage. So you explain why, qualitatively, you have anti-persistent versus persistent crack growth and exponent lower or larger than 0.5. But the main question I would like to address is how do we go from one box to another? Should we put every material in each box, or is it the picture is a bit more complex? It seems that for a 2D system, there are some experimental evidence that suggests that the key parameter to know if a system is in this box or this one is to compare the process zone size or the scale, the characteristic scale of dissipation mechanism with a microstructural length scale, typically grain size. And in case where you have a small confined process zone with respect to grain size, you fall in this class, while in the other way you will fall on this class. But the question remains really unclear for 3D materials, and this is the question I would like to address during the remainder of this talk.
May I ask a question?
Sure.
Clarification questions during the talk, not too long. All right. So can you go back, please? Well, for instance, for the fracture of 2D thin sheets, how do you break them? I mean, what is the mechanism exactly? I mean, the typical experiment that you have performed. Do you speak about slow crack growth?
Yeah, I'm talking about quasi-static slow crack growth.
Right,
yeah.
Because this type of transition, you can see also, you can have dynamical effect that may change for exactly the same type of material.
Yeah. I'm really applying. That will be. Yeah, that's a good point. I'm really applying a very slow driving to provoke crack propagation. That also is a slow process, even so that will be discussed further during the workshop. Slow driving doesn't mean slow crack propagation at every time. We will see this avalanche type dynamics, but that's a good point. No dynamic effect so far.
That may change the roughness.
Yeah, that may change the roughness, yeah. So, yeah. So, coming back on the fracture of on the statistics of the fracture roughness obtained for 3D material, I'm going to consider for this study three materials that are representative of the three classically defined main failure mechanism, namely ductile failure. Here I will take an aluminum alloy. quasi-brittle failure or failure through multiple micro-cracking. And I will take a mortar. And for brittle fracture, I will consider a ceramic. And I have scanned the fracture surface of this material at relevant length scale. And I'm going to go one step further than the value of the roughness exponent and investigate the full statistic of 8 fluctuation that I will define the following way. I'm going to consider the 8 difference delta H between a point A located on the fracture surface and a point B that is on a circle at some distance delta R. And then I'm going to move A, and I will have an ensemble of delta H value that correspond to some delta R distance within the plane of the fracture surface. And I'm going to look at the histogram or distribution of this delta H. So let's start with the ceramic. I'm going to look at the histogram of delta H for different value of delta R, from small to large value of delta R, for 3 values. And we clearly see that the distribution broaden and broaden as we go to large scale. The reason is that the correlation function we have introduced in the first part correspond to the widths of the distribution by definition. So if we have a power law increase of the correlation 2-point correlation function, we have also a width of this distribution that increase with the scale. But we see that clearly the distribution doesn't change. Actually, this is a Gaussian distribution and remain invariant as you look at larger and larger length scale. So you have a possibility with one exponent only, the one we have defined previously, to collapse all this distribution on a single master curve. This is not clear on the other materials, because as you go to small length scale, you see the appearance of fat tails, and that suggests that you cannot collapse all this distribution on the same master curve with one exponent, and we will see in the following, we need to introduce a set of exponents to make collapse these curves. So deviation to Gaussian at much smaller scale. And I will focus on these fat tails and this abnormally large fluctuation. We will see in the following could correspond to stiff cliffs on the fracture surface.
And what is delta R?
Delta R is a distance in the plane of the fracture surface that tells me I calculated 8 difference between 2 points distant by delta R within the plane.
You mentioned that you were treating it as isotropic, but you mentioned that there were 2 different exponents.
That's a good.
Are the fat tails associated with one of the 2 directions, by any chance?
No, they are not. But no, they are not.
So that's important. That's important to know.
Yeah, that's a good point. We treat here the surface isotropically as a first approximation. That's true, but the fat tail doesn't depend on the direction. Even so, the fatness of this tail slightly vary with the direction of propagation. I show you something at the end of this talk.
Can you make a comment, Laurent?
Yeah, sure.
It's clear that for larger distances you have an averaging effect, so you get more towards the Gaussian, and there's theory for small distances.
Yeah, that's okay. The fact you recover Gaussian at large scale makes perfectly sense. We're going to see after that, just by as Kai is saying, we expect the large scale to be Gaussian anyway. To explore these fat tails, I'm going to look in the next slide at the position of this large event on the fracture surface. In other words, I'm going to look at the spatial location of the largest fluctuation, of the largest jump, that correspond in practice to steep cliffs on the fracture surface. And to do it, I'm going to introduce an operator, omega, that I will define from delta H, that is the 8 difference between 2 points, that is 8 difference average over between A and B, where B is on a circle at some distance, small distance epsilon from A, taking the log. So this operator transforms the original fracture surface in some map of local intensity of the roughness, if you want. Or it's also somehow a way to see how this map is a local map, is a map of the local slopes, average over all the direction. And we clearly see large-scale features in aluminum and the mortar. We also see actually features, but at the very small scale on the ceramics. This spatial correlation of the largest fluctuation can be rationalized and described using the correlation function, the spatial correlation function of these maps omega, and defined as omega over r time omega r plus delta r when I'm going to average over the direction. And when I plot this correlation function as function of delta r in a semi-log representation, I see that indeed I have a correlated map of omega, of largest fluctuation, that decorrelate tends to 0 after some of length scale, representing the size, typical size of the largest feature I have represented on the map before. And this way I can extract a length scale for each of these fracture map, for each of these materials that correspond to the spatial correlation length of the largest fluctuation. And interestingly, this length scale corresponds roughly to an estimate of the size at which I expect damage processes and dissipative processes to take place. They are of the same, of the correct order of magnitudes. So I'm going in the following. Since I have defined two range of length scale, small length scale at which 8 fluctuations are correlated spatially, and larger length scale where I don't have this correlation of 8 fluctuations, I'm going to focus on these two range of length scale. First, interestingly, a point is that the correlation, the decorrelation of this map omega is characterized by the logarithmic function with a prefactor lambda that we will meet in the rest of the talk, lambda being the slope. And at larger scale, I have no correlation of omega. So thank you. Since now I have defined these two range of length scale that apparently shows different type of property, I'm going to come back on the concept of scaling exponent and compute the scaling exponent at these two length scales. I'm going to extend the concept of roughness exponent to multi-affine spectrum, where theta q correspond to the scaling of the moment of the q of the distribution, and the roughness exponent used previously was zeta 2 over 2. And I'm going to compute on these two range of length scale. At small scale, we see exponent as function of q close to 0.8 that are reminiscent of the mechanism discussed in the first part of this talk. At larger length scale, we find smaller exponents, smaller than 0.5. Here also, that might be reminiscent of the exponent associated to brittle failure that we encountered previously. So at large scale, we have a well-defined exponent that doesn't depend too much on Q close to 0.45 that we can understand from fractal mechanics that we know that is associated with brittle failure. And this is fairly consistent with Gaussian statistics at all scale. While at a smaller scale, we have a clear drop, clear variation of this exponent with Q. And this is also consistent with the fact that the distribution of 8 fluctuations vary with the scale. And interestingly, we can trace back this decay of the roughness exponent with the correlation of 8 fluctuations that we exhibit using the field omega. Indeed, using rather reasonable assumption on the field of local slope, we can connect quantitatively the spectrum zeta q over q with the correlation of the field omega through this formula. And here I have plugged this formula here using the lambda value extracted from the correlation of omega that provide the correct description of this multi-affine spectrum. So maybe I will skip these parts for lack of time. We can characterize the statistics and the cluster formed by this large fluctuation. I will skip that. Just I will give you the key message is that these steep cliffs we believe are a signature of damage coalescence processes, and the power law distribution of the size of this steep cliff is reminiscent of power law distributed cavities or microcrack that connect with the main crack during the process of crack propagation. And we observe robust statistical property of this object. So I will conclude. We have defined an operator omega that characterizes the height fluctuation on the fracture surface, and this has defined as a cutoff length psi that is material dependent. At larger scale, we don't have correlation of the field of omega, and we have a roughness exponent, well-defined, characteristic of brittle failure. At smaller scale, we have long-range correlation of height variation, characterized by a logarithmic drop characterized with a slope lambda, and that is consistent also with a multi-affine spectrum, meaning a variation of zeta q with q, and universal geometry of cluster, as we just saw in the previous slide. So from three different material and fracture surfaces, we can identify one common description with only one material-dependent length scale psi, and properties at scale smaller than psi reminiscent of damage, and statistical properties reminiscent of brittle failure. And so to come back on the first question on the relevance of scaling concept, I would say it's not so much the value of the exponent that provide deep insight on fracture problem, but the crossover and the cutoff lengths between the scaling behaviors. An application that will be discussed further at the end of this morning session is that this length psi is characteristic of the processes of failure, dissipative processes of failure, so they can be used to characterize these processes on the fracture surface, in particular to measure to some extent the fracture surface, the fracture energy of material. So in one word, about an experiment that explore this idea, we break a same aluminum alloy, a same steel at same microstructure at different temperature to vary the fracture energy, and in particular the size at which dissipation processes take place, and the field of omega calculated from the fracture surface of this material broken at different temperature exhibit features that depend on the temperature and that are correlated. We'll skip the quantitative comparison, but the psi extracted from this surface can be correlated with the fracture toughness and the typical size at which dissipation takes place. So I will stop here, not without thanking my collaborators that contributed to this work, in particular Stéphane Vernet and Jean-Philippe Bouchot, and I will thank you for your attention.
A very nice presentation. I have two quick questions. Have you applied this technique to look at creep and fatigue conditions? The first question. The second question is that how do you measure the roughness? Automatic way, or are you just eyes? Yeah.
Okay. So for creep and for fatigue, I didn't do so much, but actually I have some. We can see already some interesting feature. These black part are fatigue pre-crack, and we clearly see here interesting features. We clearly see actually lines where that probably correspond to cycles. So there are probably a lot of interesting things to do with this way to analyze fracture surface to get insight onto fatigue crack propagation, but it's really preliminary remarks. To scan the fracture surface, then it's really material dependent. You have to adapt your technique to the material you are considering. In a few words, you would use stylus profilometry for rocks or mortar fracture surface where the features are at large scale. What is relevant is to scan the fracture surface at the scale at which failure processes take place, so the length scale psi that is material dependent. For glass, you could use atomic force macroscopy, and for metals, you could use scanning electron microscopy. So the technique is really dependent on the material.
How about creep condition?
This I didn't explore this regime. Sorry.
I think my question is a little bit related to this one. You didn't discuss the role of plasticity on ductile failure. I mean, dislocation emission and at the crack tip and everything, and you only discuss damage versus purely brittle. So
I let this topic to Alan's talk. No, in the sense that clearly the picture is more complicated in ductile failure, where you have both a fracture process zone where action takes place in terms of damage, micro-cracking or cavities, large cavities, and a larger plastic zone where also energy dissipated by fracture, by plasticity, and at the tip of the crack. And it's definitely not clear we think that Xi measures the fracture process zone, but not the plastic process zone, and so it's not so clear to connect Xi with fracture energy for this reason. There are two length scales in ductile failure. That's a good point.
Yeah, what you discussed is two-dimensional single crack. In reality, usually if you show the first slide, there are many tensile cracks. Of course, you in your experiments you made, as I understand, special effort. So there will be one major crack. But did you try to look at micro properties? Because it's very possible that around this major crack there are micro cracks, which have needs to be taken into account.
Sure. No. All these experiments are performed with a pre-crack, a notch. So we have a well-controlled propagation of direction, so we can address this question of anisotropy. And for example, we don't have an experiment without any notch where we'll let the micro crack or the multiple crack evolve and lead to full fracture. So I don't know about your question.
Maybe, can I follow up, I think, on something related? So if you look at interfaces moving through porous media and some other models of interface motion, there's something very analogous, where if you look beyond some length scale, you see an intrinsic power law, but at shorter length scales, you get actually overhangs and other defects which give steep cliffs. If you only see a single valued height, then you just get this drop where there's an overhang. And depending upon whether you analyze the full surface or just the highest point, you get different scaling exponents in that last regime. So presumably you can't see the overhangs in this, but it would be a very similar behavior there, where then that crossover length scale in the interface problem depends upon the size of disorder or the size of stuff in the sheets, and perhaps if there were micro cracks forming ahead of the crack front, the way you showed in the first slides, that would set this lower length scale or be related to your lower length scale. Is there any evidence, if you look, that that's true?
This small scale regime is precisely associated with this process of micro crack ahead of the main crack. But what we see is some filtered information. We miss the overhangs. We have only 1 point at each location on the fracture surface. We have only 1/8. We miss the information on the overhangs, and it's the multi-affinity we see is reminiscent of this overhang structure due to percolation of microcracks or damage with the main crack. To explore this idea, we need to probably do simulation where we have information on the whole overhang structure and not only here.
I will just follow up after this comment, because it's exactly what we observed actually, and I'm going to show it just right now. Actually, it's just, I mean, I don't know, your multi-scaling regime is just probably just deviation to scaling because of steep slopes and overhangs, or maybe some other troubles in extracting really your fracture front.
No, but okay, I don't exactly. Okay, the thing we observe is that this feature that correspond to this deviation to scaling, they depend on the temperature, so they are related to the real damage processes taking place in the material, and on top of it, this multi-scaling, but also the statistical analysis of the clusters provide robust properties that tell us that it's interesting to look at there, and if we understand this property, we can gain information on the damage processes at play.
No, well, my point is just one can wonder what does that mean to extract a roughness exponent at those scales, because it depends on the order at which, I mean, how you define it, I mean, the quantity to measure it. And basically, it doesn't mean much. But the right thing is that to look at the typical scales at which you can observe different scaling regime.
Well, I think people will argue differently. In multi-scaling, without multi-scaling concept, we will not do so much in econophysics or turbulence. I mean, having the full spectrum is interesting by itself.
We'll get to hear more on that later.
So, so one thing I didn't understand, I don't know if you said it, but is there a way to understand this length scale as a material property? And also, from the analysis you presented, do I understand now why the exponents on the two different length scales different and how they're related?
Okay. So let me try to summarize briefly. We do think that this length scale is related to the first slides I've shown. That is, this length scale is characteristic of this length scale extracted from the fracture surface is characteristic of this length scale at which the front is discontinuous. And above this length scale, if you look at, if you take your glass out and look at large scale, you see a continuous front. If you see a continuous front, then fracture mechanics concept should work. In particular, this type of approach, where you have a continuous crack front, and then you can really understand using this concept, sure, having some disorder property in your material because you need some heterogeneity, you can understand the scaling properties of the fracture surface at scale larger than this one. No, at
sorry, my question was,
yeah.
Can you understand at least roughly
where does
that number for silica?
Okay.
I'll try to answer Srikanth's question. I guess when you look at these damage drops, they are random, right? I mean, the structure on them is random. However, once a damage front has appeared or a damage drop has appeared, the next one is correlated. And the next one is correlated with it. Therefore, on scales much larger than these drops, you have correlated exponents, whereas under, you have just the random thing of the local structure. This is why you have the change in exponents physically.
I have a very simple question. Usually people talk about fracture toughness in plane strain conditions, right? And it's dependent on the thickness of sample. In your modeling, thickness of sample is not present. So why?
Okay, I have considered two extremes: infinitely thin samples. That's why these two. Yeah, I have somehow separated this. I've somehow separated these two regimes you are talking about: very large, very thick sample, and very thin sample. What the separation I do is more in terms of do I have the physics of one point moving in a 2D plane, or do I have a front line propagating in a 3D space? And this really affects the scaling properties. About strain, plane strain and plane stress, I don't have really insight into the effect. I didn't study systematically, for example, that's a good point, how you go from this to this regime by changing the the width of your sample. This I don't know. Okay, persistent mean that if you start to go up, the probability to go in the same direction is larger than the probability to come back in the opposite direction. So exponent larger than 0.5.
In your fracture toughness measurement, there's a J-R curve, J versus a crack resistance curve. With your toughness or your roughness change with a J curve, can you somehow correlate the roughness with the J-R curve?
Yeah, that's a good point. We can do that. Actually, we have a bit of insight. I don't have the best example would be to take mortar fracture surfaces for which we have a clear, strong increase of fracture energy versus crack length, and we see this type of feature not as beautiful on this example, but where the scale, the value of psi locally increase with distance to the crack initiation. So you can really infer the increase of GC with crack length from the features observed on the fracture surface. You see a roughening processes, and you also see an increase of the roughness amplitude and the value of psi. Yeah.
Laura, are you saying that your Q-dependent exponent actually has only two values and changes from one length scale to another, or can I think of it as just a continuously varying exponent as a function of Q?
No, it's a continuously varying exponent as a function of Q.
So is there then a particular length scale, or
let me make it clear. The particular length scale we need to obtain this spectrum, in particular a roughly well-defined roughness exponent and a decay of the roughness exponent with Q, is to look at the scaling property at two different ranges of length scales. Looking at scale smaller than psi and looking at scale larger than psi. And psi corresponds to the correlation length of the age fluctuation. Here we stop to 3 just because of statistics. We don't go further.
So when I think about this result, it makes sense. You have like a higher length scale at which your exponent is controlled essentially by elasticity, a smaller length scale at which it's controlled by the process zone. You can pick out the process zone size, which we know exists in these materials. But when I think about these results, and with my engineering hat on, it seems profoundly disappointing in the sense that you find out there's a very common exponent for all materials that is totally independent of what their process zone is doing. But you have many, many engineers running around doing fractography, looking at the surface and trying to infer from the fracture surface what's going on in the process zone. So is this saying that really there's not information that tells you the details of the process zone, or is it telling us that we're looking at the fracture, looking at the affinity, or is not the right thing to look at, right?
That's definitely the information you have on the fracture surface is filtered, and the remaining information is probably not going to tell you the full story. But I would say give to this field 30 more years to have more insight on the material dependent properties. Here there is at least one length scale we can extract. That seems obvious from an engineer perspective because it's well known that we have a process zone at some well-defined length scale. But maybe from the spectrum and from other properties, more complex and refined statistical property, we get more insight. For example, how to separate fatigue crack from quasi-static crack. This is really the challenge for the coming years.
Okay. I'm consciously going a little over since we have a long break, and as long as there are questions. Our next talk will be by Stéphane Santucci on self-affine structure and avalanche dynamics of crack